Hello, and welcome back to a video series on MAC 2311 Calculus 1. My name is Sean Perry. These are guided notes number 3 in the series, Numerical Limits. If we're given a formula for a function f of x, then we can sometimes figure out the limit by plugging in values that approach a certain value from the left and the right, and see what kinds of patterns we can discern. Now, for the problems given in your homework, the values of x, which approach a certain value, are going to be given to you. You're going to see a sequence of x's which get closer and closer to a central value c, both getting closer from below, that is to say the left limit, and from above, which will give us the right limit. And we'll record these values in a table. All you have to do is substitute the values in the table into the formula given for f of x, and then look for certain patterns. However, you should anticipate that for the vast majority of the problems, f of c, where c is the value we're approaching, is going to be undefined. There's going to be a divide by zero problem usually, but you're not going to be able to just plug in values at c into the function f and get a number. Now, if we get an undefined value, we just have to write DNE, or does not exist, into our table. But keep in mind that we might still have a limit which exists, even if the value f of c does not exist. Likewise, you should also keep in mind that we will only get an answer for our limit if we have both a left and right limit, and these are equal to each other, in which case they're equal to the overall or two-sided limit as well. Below, I'll walk through some examples. I also want to show you how you can save some time by using list operations on a Texas Instrument calculator for plugging in numbers to the same function over and over again. We will have to do a little bit of work when we plug in our value c, because that's going to be undefined, and that bad apple can sort of spoil the whole bunch, so to speak. But this will still save us time for all of the regular values of the function. Now, that's going to be something you can do in my class, because I'm pretty permissive with what kinds of technology you can use, especially in terms of graphing calculators, as long as they don't have a computer algebra system. This may vary from professor to professor, and with good reason. Some professors don't want you to use calculators at all, and I think that's fine. I think there are certain things to be gained and lost in each kind of strategy. All right, so let's jump into an example. This one says, let's consider f of x is equal to sine of 9x over 9x. We talked about this kind of problem in the last video. We should notice that we already anticipate the value of f of c, in this case f of 0, to be undefined, because that would put a 0 in the denominator. And so for this value, I will just mark DNE. But let's see what that would look like on the calculator. What kind of error would we get when we plug in 0 into this kind of function? So for these kinds of situations, I like to pull out a Texas Instrument emulator. Let's first type in our function. Notice that I put the denominator in parentheses. This is because your calculator would perform order of operations and just divide by 9, then multiply by x, if I had not typed that in. The x can be found here, but any letter will work for what I have in mind. Notice that it's given us a number and not some other expression. That's because calculators which do not have computer algebra systems, but which only have computational systems, must substitute a number in for x. If I asked it what's x by pressing x and an enter, it currently has x set to 10, and that's why it's giving us a number here. It's actually doing sine of 90 over 90. Now, what we could do instead is tell x to take on a different value. I've done that by pressing 0, then the arrow button, which is store as and not convergence, and then our x key again. Now I'm going to go back to sine of 9x divided by 9x by pressing second enter a couple times to get me back to that line without having to retype in a few things. This time it's going to treat x as a 0, an error. Error divide by 0. This is something that we're going to see frequently when we try to plug in values into these functions. We will get a divide by 0 error for a great many of them. And what we're going to learn is that that's only the beginning. We may still have limiting values, and this might be a point discontinuity. Now, notice the numbers that we have to plug in here. We need to plug in negative 0.1, negative 0.01, negative 0.001, negative 0.0001. So notice we're getting smaller and smaller in magnitude, but we're still negative. That means we're approaching 0 from the left. And likewise here we have 0.1, 0.01, 0.001, 0.0001, and that is getting smaller in magnitude, approaching it from the right. In either case, we are approaching this value 0, and this is why we are able to figure out these limits here. This is what is the limit when we approach negatively, when we approach positively, and when we approach from both sides. So this is the left and the right, and both of them. So to figure these out, let's fill out this table here. And one of the quickest ways we could do that is by using our calculator. Now, we could just plug those numbers in for x. I could take this expression, and instead of x, I could either store a new value as x, or I could just type these numbers in. But that's going to take even more time because we're going to have to do that each time we want a new value. Wouldn't it be great if we could just do that all at once? So here's what we're going to do to affect that. I'm going to clear this. I'm going to click on the button that says Stats and then Edit to edit my lists. Now, I already have some lists here. If we'd like to get rid of what's written in those lists, there's a command for that. I'm going to go back to the main screen. I'm going to go to Stats and then down to Clear List. And now I'm going to tell it which lists I want it to clear. I want it to clear the first 3 lists, and lists on the calculator get a special name with L's in front. So we want to press L1 by pressing second 1 here. And we could do this one at a time, or we could do them all at once by typing in L1, L2, and let's say L3 as well, all separated by commas. And when I do this, clear list will say done. Now if I go to Stats, Edit, we can see it's cleared off those lists. So what I'm going to do now is I'm going to type in order these values except for 0. If you typed in 0 as well, it would crash the entire operation that we're about to perform. So we want to leave this one out. So I go in here and I'm going to type in negative 0.1, then negative 0.01, negative 0.001, and finally negative 0.0001. Notice that for this it says negative 1 e negative 4, but this is just scientific notation, negative 1 times 10 to the negative 4, which is the same as this value. It's just written here in engineers' scientific notation. Let's type in the other numbers as well on this side. Let's type in 0.0001. We see that's the same as this one, but positive, 0.001, and so on, until we complete this list. Once I typed all 8 of those values in here, I am ready to calculate the rest of the values in the table. What we're going to do is we're going to call up, using second enter, our last command with the sign of 9x divided by 9x here. And then what I'm going to do is I'm going to replace x. I'm going to get right on top of it, and I'm going to press second L1 to replace it with L1. Over here, same thing. Now when I press enter, this is going to actually give me a bunch of values. It's going to give me one value for each entry, but it's kind of hard to read in this format because you have to scroll over a bunch and there's like so many decimals. So what's easier to do, let's press second enter again and bring up our last command. I'm actually going to store this someplace that I can read it. By pressing second L2, I can store this list as L2. Now, this is where the payoff is. When I click here, it quite simply just lists off all the answers to what goes in the table. And you can then follow the particular rounding instructions to just copy this over. So I'll do that now. Notice that this third entry, 0.999999, when we round this to 4 decimal places, it's already essentially 1. And here we have something which, to the calculator's best ability, just looks like 1. And so it's written this as 1. If we go over, we could see these to more decimal places, and we can see that 1 is actually 0.9999998, blah, blah, blah. But that's pretty close to 1, right? At least out to 4 decimal places it is. Likewise, for these values, positive values down here, we have the same numbers again, just reflected. And now from this table, we can answer these limit questions. As we approach from the left, we seem to be getting closer and closer to a value of 1. Out to 4 decimal places, it's exactly 1 for the last 2 of them. So this would be 1. And in the exact same way, if we took a look at what happens as we approach from the right, we get values which are increasingly close to 1 until they're indistinguishable from 1 out to 4 decimal places. And so this is also 1. Because these two values match each other, we have a two-sided limit that exists, and it is also 1. And there you have it. Let's take a look at another example. Here we have f of x equal to the square root of x minus 5 divided by x minus 25. The first thing we're going to want to do is put these x values into our list. Let's also notice that if we plugged in 25, we would get DNE. Why is that? Because the denominator would be then 25 minus 25, which is 0. Zeros in the denominator always make this expression undefined, and so we write does not exist. And let's notice the x values. We are adding 9s to the end of each decimal here. That's getting us closer and closer to 25 from values below 25. Likewise, if we looked over here at 25.1, then 25.01, 001, 0001, and so on, that's going to get us closer and closer to 25 from above. So now let's go and edit our list. By the way, we could just edit it right here in this table, but just for your own edification, let me show you one other way that you can edit lists on the calculator. This is nice because it doesn't require us to clear any entries, but some people prefer one method or another. I think both have their advantages. So what I'm going to do is I've typed an open curly brace, that's second open parentheses, then the first number, 24.9. Now I'm going to type the next numbers separated by commas. So 24.9, comma, 24.999, and finally 24.9999. And that's going to finish our approach from below. Now let's approach from above. So I'm going to just keep copying like this because I want my table to look like this table. So let's now do 25.0001. That'll be the final number on our approach from above. And now 25s with just fewer zeros and then a 1. So 25.001, 25.01, and just 25.1 to finish it up. So now we put a closing curly brace. It has to be a curly brace and not a parentheses. Press second and then parentheses. And now we're going to store that as list 1. So second 1 gets us L1. It needs the L name. It can't just be a letter. So there we go. And now notice that if I went back to our stats edit screen, that's now my list 1. Notice that even though the display is 25 here, it's still 24.9999 versus 25.0001 respectively. So now let's actually populate L2 correctly. So we want to type in our expression here. So I'm going to put in parentheses the numerator. Now the numerator was the square root of x minus 5. So we're going to do the square root. You can find square roots right here of the values which are in L1. And I do that just by calling L1. Leave the square root, subtract 5, and then put this whole thing in parentheses. Remember, a quotient bar puts imaginary parentheses around the numerator and the denominator. We need those when we're typing this in. Now, if your calculator, when you press quotient, makes a pretty print kind of a fraction, okay, it'll do that for you. But many calculators will require these parentheses. So on the bottom, we had x minus 25. So we're going to put L1 minus 25 here. And that's going to give us all of the values for this table so that we can read them more easily. Let's store this as L2. And we go to Stats, Edit, and we can just kind of read off our answers here for L2. So first off, we have 1.001. So I'm just going to copy these over straight away right now. And notice that some of these rounded to 4 decimals are absolutely just 0.1, even if they continue a little bit longer and have some more decimals after, but they would round to 0.1 exactly. So I'll just put the fully rounded 0.1 here when I complete this table. If we round, that's going to get us 0.1. And from here, we can answer our limiting question. Even though the function value does not exist when x is equal to 25, we still have a limit which exists as we approach from the left and right. In both cases, that gives me 0.1. And so our two-sided limit, that is to say without a plus or a minus right here, is 0.1. Now, we'll talk about this much more in the next video, but there's actually a way that we could have seen that this had to be the case without plugging in any numbers. Before I mention that, I'd like to give an example of what's going on here. The example I want to give you is x over x. Now, you might know that x over x is 1, but that's only true if x is not equal to 0. If x is equal to 0, then we have 0 over 0 here, and so that's actually going to be undefined or does not exist. When we look at graphs of this function, we can see exactly what's going on. We have a flat line at 1 and a hole at the point 0, 1, where there is no value for the function output. So even though it looks like we're at a constant value of 1 as we approach from either direction, and so our limit value exists and is equal to 1, the function value does not exist at that point. That's very similar to what's going on here in this problem that we just looked at. Well, if you think about it, this is almost a difference of squares. It's just not a difference of perfect squares. That is to say, this isn't x squared minus 25 on the bottom, but one could look at x as being the square of something. It's the square of the square root of x. And so with that little hint, could you factor the denominator? What about like this? If you didn't see that, FOIL it out and confirm that we would actually get the same denominator. And what was the advantage of that? Well, the advantage is that upstairs in the numerator, we have a square root of x minus 5. And now that's free to cancel, and this just gives us 1 over the square root of x plus 5. Now, that's only true when x is not equal to 25. Because if x was equal to 25, well then, you would have a 0 in your denominator, wouldn't you? But when it's not equal to 25, this cancellation does happen. So for all values around 25, this happens. And notice now, there really isn't a problem with plugging in your value of 25. 1 over square root of 25 plus 5 is 1 over 10, which is exactly 1/10, which we got before. So this would be an analytic way, or a way which uses our algebra rules to establish the value of a limit by finding out what the function is everywhere except for the troublesome point. We'll talk much more about that in the next videos. I just wanted to remark that it's an interesting way we could have proceeded with this problem that confirms what we also learned numerically by plugging in values. Okay, let's move on to the next one. Alrighty, so here we can see we're going to be asking about what happens when x approaches 9. And we can see right here that if we were to plug in 9, we would get 0 in the denominator, which would be a problem. So that tells us right off the bat that this does not exist for our middle value. So what I'm going to do now is plug in all of my values for x into a list. This time, just for fun, I'll work inside of this table. We are looking at 8.9, and we're going to do 8.99, and we're just going to keep on that pattern of adding 9s until here on our fourth value, we have 8.49s. Just above 9, let's do 9.0001, and then with a decreasing number of zeros, we're sort of backing away from 9. So this would be a right approach if we were to go 9.1, 9.01, 9.001, 9.0001. But we're looking at it sort of from both directions, right, where it meets in the middle. And now we're going to populate L2 with the outputs. So let's quit, go back to our main screen, and now let's type in our function here with an L1 instead of an x. So here I have 6 divided by parentheses, second one is L1 minus 9, and then we want to square that denominator. There we go. And then all of this is going to give me one big output, so I'm going to make sure that I store that someplace I can read it, like how about L2, and there it goes. Okay, so let's go to Stats, Edit, and look at what our values are. Okay, so we have 600, then we have 60,000. And then we have 6e6. Now remember, that's 6 times 10 to the 6, that's 6 million. So we might actually see the pattern if we wrote this all in scientific notation. This would be 6 times 10 to the 2, 6 times 10 to the 4, 6 times 10 to the 6, 6 times 10 to the 8th, and so on. So let's write all this down. This was 600, this is 60,000, this one here is 6 million, and then finally 60 million. The same thing is happening as we approach from the right. This was 600 as well. And we actually know this because this function has a square in the denominator, so it's taking whatever these differences are and squaring them. And positive or negative numbers, if they have equal magnitude, they have the same square. So we already know these values are going to be symmetric on this side. All right. So once we've copied over these digits into our table, we can now estimate the limits. So our limit as we approach from the left, well, what's the pattern here? It seems like we're just adding zeros. When we get closer and closer, this thing gets another 0 added to the end. When we add another 9 to the end of the input, we added another 2 zeros on the end of our output. Now that's telling me that our output is increasing without bound. So it's shooting off towards positive infinity. Likewise, on this side, it's shooting off towards positive infinity, and that means overall it's going towards positive infinity. Please keep in mind that if you had something like 1 over x, the right limit goes towards positive infinity, but the left limit goes towards negative infinity. And so in this case, the limit would not exist because we consider negative and positive infinity to be two different things. But for this current example, both the left and the right-sided limit are going towards positive infinity, and that's what makes the two-sided limit also equal to positive infinity. Alrighty, here we have another example. We're actually looking at limits as x gets larger and larger in magnitude. For this first one, what you're looking at is as we go to the left, it's getting bigger in magnitude and is negative in value. So we consider these to be examples of a way that x might approach negative infinity. Of course, it's not getting closer to negative infinity, but it is decreasing without bound, getting larger and larger in magnitude while having a negative value. And so that's going to indicate for us a little bit about the long-term behavior of f of x. Likewise, in the second table down here, we are getting larger and larger in magnitude. So we're going to use that to discern what happens to f of x as x approaches infinity. And we can again use our trick with plugging in list operations. So let's do this as negative 10,000, negative 1,000, negative 100, negative 10. Now let's look at the other side. We have 10, 100, 1,000, and 10,000. And now we're going to want to plug those into this function. So let's quit back out to our main screen, clear the board, and clear our minds. Looking at our function, we have a numerator x plus 5. So in parentheses, I'll put L1 plus 5, divided by, again in parentheses, we put our denominator, which is x plus the square root of 4x squared plus 5. So L1 plus the square root of 4 times L1 squared plus 5. Close our parentheses. And now we have a denominator which looks just like our denominator here. Store this as L2 and then press enter. Let's go to stats, edit, and take a look at our chart here. So here we have negative 0.9995, rounding to 4 decimal places. And I'm just going to type in all of these numbers as they go down. Now here we can start to see some trends forming, but I honestly don't think that I would be able to make a guess with just the data given. Sometimes you're going to need to go a little bit beyond the chart here, but maybe you can see what's happening. Notice that we have this pattern of 9s starting to form, and that's seeming to hold consistent here. Let's plug in some negative, even bigger number and see what happens. One way that I can do that pretty painlessly is by taking my very large number I want to try out, like in this case, I'm going to try negative 100,000, and store it as a variable. Let's store it as x. Now I'm going to go back to the line where we defined L2, and I'm going to just replace L1 with an x. This is going to let me evaluate the function at one point. I don't want it to store it as L2 anymore, so I'm going to delete that part. But I'm going to go back through my equation, and everywhere that I see an L1, I'm just going to replace it with an x now. And this is going to let me evaluate this function just at this one point. And let's notice that gives me 0.99994, and then more 9s. And so here we can see the pattern is confirmed that we really are looking at a bunch of 9s repeating. So we could come up with a conjecture here about what is the limit as x approaches negative infinity. Well, it looks like it's going to be 0.9 repeating. And 0.9 repeating is a very fancy way of saying 1. If it's 0.99999 all the way down, that is essentially the exact same thing as 1.0 repeating. There is no difference. The 0.9's repeating goes all the way to infinity. And so the difference between it and 1 is nothing. One way that you can confirm this is in fact true is 1/3 is 0.3 repeating. And so if you multiply that by 3, you just get 1, which is 0.9 repeating on this side. Now let's check out if we can confirm that this pattern of repeating 3's happens as we go positive. So here we saw some good evidence of that. We have a weird random number, then 0.35, 0.335, 0.3335. I wonder if that repeating pattern continues. So let's confirm that by plugging in some large number in for x here. What is, for example, f of 100,000? So I'll just take 100,000 and store it as x. And now I'm just going to press second enter a couple times to bring up my last line where I evaluated the function. So here's my function. I press enter to evaluate. And we can see that it continues the pattern, 0.33335. And so we have a bit of a conjecture here too. We have that the limit of x as it goes towards positive infinity is going to give us 0.3 repeating, which, as discussed, is in fact 1/3. So our answers here are 1 and 1/3 respectively. Let's do one more example. This is going to be something very similar to our split asymptote 1/x, my favorite hyperbola. Here's a quick Desmos graph. If we look over at 9, we can see that there is in fact a vertical asymptote at that point. And so as we would approach from the left, we would get positive infinity. As we approach from the right, we would get negative infinity. And so the overall limit at 9 would not exist. But our question is actually asking for what happens as x goes to infinity. We're talking about the horizontal asymptotes here. And you can sort of see, just from the graph anyway, that it looks like we have a horizontal asymptote at 2. So I'll show you how we could approximate that numerically. So now we just want to populate list 2 with the function outputs of plugging in these values. So I'm going to quit, back to the main screen, and then type very carefully this function in with an L1 substituted for x. And to get this where we can read it, let's store that as L2. So now let's just copy these over from this chart into these tables here. And remember, as we are approaching negative infinity, we're reading along values going greater and greater in magnitude, but in the negative direction. So this is looking like approaching 2, and also 3, 2.011, 2.001, 2.0001. As we go towards infinity, we have our function value go towards 2 as well. Now, how might we have been able to do this analytically? This expression in terms of a single rational function, get like bases, by multiplying by x minus 9 on the top and bottom, and then simplifying by distributing and collecting like terms. Now, as you should recall from pre-calculus or algebra class, your rational functions have horizontal asymptotes equal to the ratio of their coefficients if the degree of the numerator and denominator are the same. So these are both of degree 1, and our coefficient ratio is 2 to 1. And that lets us know that we have a horizontal asymptote at y equals 2. All right, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.